Today we're diving into a really cool quirk of physics, something that happens inside every single X-ray machine. And what's amazing is how medical pros have learned to turn what looks like a flaw into an incredibly useful feature. All right, let's kick things off with a fundamental problem, a real engineering headache. To get X-rays, you've got to slam electrons into a metal target at insane speeds. Now this creates a ton of heat, enough to literally melt the machine. But here's the catch. For a sharp, clear image, you need that X-ray source to be super tiny and precise. So how on earth do you get both? How do you get a tiny focal point without the whole thing just melting?
Well, the solution is actually pretty elegant. It all comes down to a simple but super clever trick of geometry.
And here it is. The answer is to angle the anode. That's the metal target the electrons are hitting. So instead of it being flat, facing the electron beam head-on, they tilt it. Usually it's just a slight angle, somewhere between 5 and 20 degrees. But that one tiny change, it has two huge benefits.
Okay, so let's really break this down, because this is where the magic happens. By angling the anode, you really do get the best of both worlds. So on one hand, you get much better heat management. See how tilting the target actually spreads the electron beam over a larger surface area? More area means the heat gets distributed, so the anode can take a lot more punishment without melting. Awesome. But then, on the other hand, look at what the patient or the X-ray detector sees. Because of that angle, the source of the X-rays looks way smaller than it actually is. We call this the effective focal spot. And a smaller spot means a much, much sharper and clearer image. It's brilliant, right?
But, like a lot of clever solutions in engineering, this one has a side effect. It's this unavoidable consequence, a quirk of physics that actually changes the X-ray beam itself.
And that side effect has a name, the anode heel effect. So what is it? Simply put, it's an unevenness in the X-ray beam. The intensity isn't the same across the whole beam. And that's because the anode target itself ends up absorbing some of the X-rays it creates.
And you can see the result right here. The X-ray beam isn't uniform at all. You can see it's way more intense on one side, the cathode side, where the electrons come from, and it gets weaker on the other side, the anode side. It's a pretty significant difference.
So why does this happen? This diagram explains it perfectly. Okay, so X-rays are created at different depths inside that angled target. Now, think about the ones generated over on the anode side, what they call the heel of the anode. For those X-rays to get out, they have to travel through a whole chunk of the metal target itself. And, well, on that journey, some of them just get absorbed. They never make it out. It's really that simple. The target is, in effect, blocking some of its own X-rays.
Okay, so at this point, you're probably thinking, well, that sounds like a bug, right? An uneven beam has to be a design flaw. And you'd be right to think that. But in the world of medical imaging, it's actually become an incredibly powerful tool.
So instead of trying to fix it or work around it, radiographers lean right into it. They use it to their advantage. They'll actually position the patient so that the thicker, denser parts of their body are lined up with the more intense side of the beam, and the thinner parts, they go under the weaker side. It's all about matching the beam to the body. The whole goal is to get a really nice, even exposure on the final image. And there's a super simple way to remember how to do it. The mnemonic is fat cat. It just means you put the fatter part of the body under the cathode. Simple as that. The cathode side has the more powerful beam, which is just what you need to penetrate denser tissue.
And here are some perfect real-world examples. Let's take the thoracic spine, your upper and mid-back. Down by your abdomen, you're a lot thicker than you are up at your neck, right? So they position you with the powerful cathode side over your abdomen and the weaker anode side over your neck. Same idea for a femur X-ray. The hip is way denser than the knee, so hip goes under the cathode, knee under the anode. Using this trick helps them get a perfectly balanced image, every time.
And what's even cooler is that this effect isn't just a fixed thing. Its intensity can actually be tweaked. It's a variable that designers can control just by changing the angle of the anode.
Just look at the difference here. The steeper the angle, like that 6-degree anode, the more of the anode material the X-rays have to travel through to get out. That means more of them get absorbed on the heel side. The result? A much bigger difference in intensity across the beam. So a steeper angle gives you a much stronger heel effect.
So here's the key takeaway. It's an inverse relationship. The smaller the angle, the bigger the heel effect. And this is great for manufacturers because it means they can design different X-ray tubes for different jobs, depending on just how much of this effect they want to take advantage of.
Okay, so we're dealing with some pretty complex physics here. And when patient health is on the line, you absolutely cannot have things going wrong.
So how do you make sure these incredibly sophisticated machines are working perfectly, day in and day out?
Well, that's where the critical field of quality assurance, or QA, comes into play. Think of it as a comprehensive program of checks and balances. Its entire purpose is to make sure every single piece of X-ray equipment is performing exactly the way it was designed to, giving doctors the best possible image with the absolute minimum radiation dose to the patient.
And we're talking about a whole battery of really rigorous tests that have to be done on a regular schedule, at least every 2 years. Medical physicists and technicians will come in and check literally everything. Is the timer accurate down to the millisecond? Is the beam perfectly aligned? Is the radiation output consistent every single time you press the button? They even check to make sure no extra radiation is leaking out of the tube housing. It's incredibly thorough. And the tolerances they work with are razor thin. Take beam alignment, for example. The central X-ray beam has to be perfectly perpendicular to the image detector. The margin for error? Less than 1.5 degrees. If it's off by any more than that, you start getting distorted images, and that could, frighteningly, lead to a misdiagnosis. So it has to be perfect. When you step back and think about it, the anode heel effect is just this beautiful example of human ingenuity in medicine. You start with what is basically an unavoidable side effect of a really clever design, and instead of fighting it, you transform it into a practical, useful tool that helps radiographers get better images every single day. It's just such a great reminder that sometimes the key to innovation isn't about creating something flawless, but about deeply understanding a system's limitations and then turning those limitations into advantages. It really makes you wonder, doesn't it? What other bugs in science and technology are out there, just waiting for someone to find a clever way to turn them into an essential feature?